Right, Bismillahirrahmanirrahim. Assalamualaikum warahmatullahi taala wabarakatuh, everyone. So let's start the class with the Ummul Kitab Al-Fatihah and doa. Bismillahirrahmanirrahim. Iyyaka wa iyyaka nasta'in. Ihdinas siratal mustaqim. Siratal ladzina ghairil maghdubi 'alaihim waladdallin. Salli wa sallim. Sallim qawqaw. Okay, Bismillahirrahmanirrahim. Right, so the topic for this week, which is week 10, okay, the topic is sound, okay. It falls under vibrations and wave, but the topic is sounds, okay. So let's look at the learning outcomes, okay, a little bit uh, few compared to what we have learned last week. Okay, in here we have about 12 plus with another 9, which is altogether is 21 learning outcomes. Okay, I have compiled it all together. So the topic is in the chapter 14 in your textbook, which is sound. Okay, so uh, so as the first thing is you should know that the sound wave are longitudinal wave. Okay, so in this topic we will explore different characteristics of the sound wave, okay, which happen to be in the process of compress and stretch of the air molecule. Let for example, how they are produced, what are they, how they travel through matters, and we also how sound wave interfere with each other. Okay, so this is some musical instruments that is a source of the sound, one of the source of the sound, which is how to we can we produce sound in many different ways. Okay, right. So we start with the tuning fork. Okay, so I happen to be in our laboratory session. Okay, in the for specifically in a simple harmonic motion experiment. So you will use a tuning fork. Okay, so the precise term is a vibrating tuning fork. Okay, so as you can see, the figure on the left and on the right, you can see there is a high density region and also a low density region. Okay, so sound wave are longitudinal wave traveling through a medium like air, of course. And let's look at the tuning fork. Okay, so this is a tuning fork I'm telling you, which is a common device for producing pure musical notes. Okay, producing pure musical notes. How do I know? So when we hit a tuning fork somewhere around here, somewhere around here, so it actually vibrating. When the tuning fork vibrating, it produces a sound. Okay, we cannot hear ting, it's not the sound. Okay, but when you take the tuning fork closer to your ear, you can hear it actually producing some sound, not similar to each, because we have a set of tuning fork with a different frequency, of course, and because of the different in frequency, we can see a different in sound, right? So a tuning fork consists of two metal prongs, like this one, two metal prongs, or should we call as tins, that vibrate when struck. Okay, when we hit the tuning fork, it can vibrate. The vibration disturbs the air near them, so it disturbs some air, as shown in the figures. Although the amplitude of the vibration is very exaggerated. Okay, when a tin swings to the right, as in the figure, okay, swings to the right like this one, okay, figure on the left, the air molecules in front of the tin are forced closer together than normal. Okay, this region of high molecular density um, and high air pressure is called a compression. So that is what we call as compression of air molecule. This compression move away from the fog like a ripple on a pond. Okay, let's say, for instance, you can see when you throw a stone onto the pond column, okay, you can see a pattern of wave that is okay, we call that as a ripple effect. Okay, it actually it is small. Okay, we just hit with a small stone, but regardless of the stone is small or big, okay, it created some ripples effect. That means it created some wave that move away from the sources. Okay, when the tin swings to the left, okay, for instance like this one, as you can see in the figure, okay, the molecules in the air to the right of the tin, okay, this one, the right of the tin, okay, spread apart, and so the density and air pressure in this region are lower than normal. So before this we have high density region. So in this case, okay, when it vibrating, okay, so when the things move to the left, so the density and the air pressure is lower. Okay, of course, this region reduce density, that is what we call as rarefaction. Okay, on the high density region, we call it as compression, compress, and when the air pressure or density lower than normal, we call that as rarefaction. Okay, rarefaction. Okay, now we go to the next slide. Right. So as the tuning fork vibrates to vibrates, a series of compressions and rarefaction. Okay, look at the term used, compression and the rarefaction move outward, okay, away from the fork, right? And we have a figure A and a figure B over here. Okay, this is in figure A we can see that the tuning fork vibrates and a series of compression and the slide in the very um, uh, mild color, okay, a little bit mild color compared to the striking one. The striking color is a compression, is where the air molecules compress, and the rarefaction you can see here a little bit mild compared to the striking one. Okay, you can see a series of striking and a mild colors of this color. You can see on your slides where it actually projects some compressions and refractions. Okay, so on the figure B, you can see that the crest of the wave, the crest is what we call as puncak, okay, of the wave correspond to the compression. So it is actually at the compression part, okay, which means that on the color is striking, okay, it actually a a correct where it actually have some pattern of crest. Okay, so in the sinusoidal, okay, there are crests and there are also a throw. Okay, crest and throw. So the compression is specific for a crest, right? And throw is the rarefaction. Okay, when the color is mild, a little bit mild compared to the striking one, so it is actually is a pattern of rarefaction. Okay, as so what is it all about? As the tuning fork continues to vibrate, a succession of compression and rarefaction, okay, forms and spreads out of it. Okay, it can spreads through the air, and the air pattern is a bit like what is shown in the top figure here. Okay, we can use the sinusoidal curve to represent a sound wave. Yeah, as you can see in the bottom figure, say this is a sinusoidal graph. Okay, okay, now we have seen that the motion of air molecules near a vibrating object is back and forth between regions and compressions and also refractions. Okay, So this is actually a vibrating object. This motion is characteristics of the longitudinal wave. And as you can see, in the longitudinal wave, okay, the motion of the element of the medium is a back and forth along the direction in which the wave travels. So if the wave is traveling forward, okay, in the forward position, so the if we can take one atom, okay, the motion of that atom is also on the parallel to the displacement. Okay, it's contra to the transverse wave because the longitudinal wave, the medium or the atom, if we can take one part of it, is actually as the same direction as the displacement. On the other hand, okay, as mentioned, the transverse wave, okay, the vibrations of the element are at the right angles to the directions of the traveling wave. Okay, so there are three categories of the sound wave. Okay, we have an audible wave, okay, which is the longitudinal wave that lies within the range of sensitivity of the human ear, approximately about 20 to 20,000 hertz. So it's actually audible wave. That means we can hear as a human being. Okay, okay, in a region of 20 to 20,000 hertz. That is the range of frequency that the human can hear the wave. So we can actually hear the sounds, right? So that is also the number two, infrasonic wave, which is a longitudinal wave with a frequency below the audible range. Below the audible range. For example, we have an earthquake wave. Okay, earthquake wave is the examples of infrasonic. And also we have an ultrasonic wave, which is a wave that is a longitudinal wave, again, because sounds considered to be all in longitudinal wave with the frequencies above the audible range for human and are produced by certain types of whistles. Animals such as dogs can hear the wave emitted by this whistle. Okay, in this case, okay, normally for those people, okay, um, not many of us have played with dogs. Okay, but for those who have dogs, okay, they have some whistle that very sensitive to them. Okay, because dogs can hear the wave or specifically the sound that have a very high frequency. Okay, so ultra is the region of, okay, we can say that the audible is in the middle. So before that is the infrasonic, and then after the audible is what we call as ultrasonic. So because we cannot hear the ultrasonic wave, that's why when we, okay, try to whistle this particular sound, okay, the dog, for example, the dogs, okay, it can respond to that sound because it is in their regions of hearing. Okay, so it's very uh, special whistle. Right. So an alternating voltage applied to the phase of piezoelectric. So this is the application of ultrasound. Okay, that means the sound can be applied to the system of ultrasound. Okay, so I don't want to focus on this part. Okay, in ultrasound of image, that means for those mother that is that want to use ultrasound as their application in order to see the conditions of the fetus in the womb, so they use an ultrasounds. Okay, and then of course, uh, because of that, we need to see the significance of the speed of sound. As you can see, the speed of sound are not um, are not the same in every region or every medium. Okay, for example, we have a speed of sound in air at a 343 meter per second. Okay, 3 meter per second as the speed of sound in air. Okay, now we look into the speed of sound in various examples. Okay, it's a 343 or in air, it happen to be 331. Okay, 331, 343 is for speed of sound in vacuum. Okay, but of course in vacuum we cannot hear anything because it doesn't have any air. So therefore, speed of sound in air, we should use the 331 meter per second. Okay, as you can see, there are several mediums. For example, we have this fluid. Okay, when sound travel in fluid, what I call fluid, because uh, sound travel in gases and also liquid. Okay, so as you can see, the speed of sound is much higher in solids than in gases. Okay, and this is because the molecules in solid interact more strongly. Okay, as you can see, the molecules or the atoms. Okay, while comparing solids, liquid, and gases, of course, okay, you can see solid. The molecule in solid is close to, okay, to each other compared to gas and liquids. Okay, so that's why a speed of sound in solid will give you higher value compared to gases and liquid. So imagine striking a long steel rail with a hammer. Two sound waves are produced, one moving through the rail and slower wave moving through the air. If someone presses their ear, okay, we put our ear closer to the rail, they will first hear the faster sound moving through the rail, and then the sound moving through air. So that is why, because of in air it contains some molecule. So in the solid also there is a molecule. The molecule in solid is more arranged closer compared to in gas or in air. So that's why we are saying that the speed of sound in medium will have a different value by will have a different value, but we need to take into consideration of the arrangement of the molecule. Okay, so this is the table list the speed of sound in. You can hear the speed of sound in solids, for example. Okay, before this we have speed of sound in gases and liquid. Here is the solids. You can look at the value. It's very big, the thousands of it. Okay, thousands meter per seconds, because the conditions of the molecules. Okay, so the speed of sound depends on the temperature of the medium. Okay, for sound traveling through air, the relationship between the speed of sound and temperature is shown here, where 331 meter per second is the speed of sound in air at 0 degrees Celsius, which is T is the absolute Kelvin. Okay, absolute Kelvin temperature. That means you need to convert from 0 degrees Celsius into the Kelvin. Okay, into the temperature, because 0 degrees Celsius is considered to be 200 and considering about let's say you use it's quite 27, for example, okay, because 0 degrees Celsius is equivalent to 273 more or less 273 degrees Celsius. Sorry, 273 Kelvin. So when you add up, okay, you add up to 200 to the room temperature, we are saying that the T will become at about 293. Okay, the room temperature is taking here as 20 plus, okay, 20 degree plus. So when you have at the room temperature 20 degrees Celsius, so the temperature in absolute temperature, which is in the Kelvin mode, in the Kelvin scale, is at 293 Kelvin. So that's why the speed of sound, as you can see, in air at 0 degrees Celsius, we took at 331. But the speed of sound in air at the room temperature, so precisely we took about 343. So as I mentioned earlier about the speed of sound in air, it should be 343 at the room temperature. Okay, at zero temperature it is 331. 31. Right. So remember our tuning fork. Okay. As the tins of tuning fork move back and forth through the air, they exerts a force on a layer or air and cause it to move. Okay. It moves, it vibrates, and it creates some compression and rarefaction. Where compression and rarefaction is, if we can imagine in the sinusoidal graph, so the graph should be have crest and also throat. Correct. So in other words, the tins do not work on the layer of air. Okay. Energy is lost in the form of sound and also friction as the tin bend, so the vibration of the fork slowly dies out. So occasionally, okay, when you hit the tuning fork, okay, it doesn't stay that way for a longer time. As we move or as we can hear through our ear, okay, the sound will fade, okay, akan semakin berkurang, will fade, will have some damp motion, or it will dampen. Okay, it will die slowly. Okay, the average, so you can see here the average intensity of the wave. That means we took the highest one and the lowest point, so we took as the average intensity of a wave on a given surface is defined as the rate at which energy flows through the surface of a delta E, to a surface of delta E over a delta T, divided by the surface area, this one, surface area. The direction of the energy flows is perpendicular to the surface at every point. Okay, a rate of energy. Okay, a rate of energy is I see here. This is the energy over time. So that is actually power. Okay, energy over time is power. So we took power, we put it here. So a rate of energy is power. So we can write this in another way as the intensity is what we call as power per unit area. That means you put a lot of energy over some certain times, over a certain times, and then over an area, there is a some intensity. At a frequency of 1000 hertz, 1000 hertz, the faintest sound the human ear can detect, our human ear can detect the faintest sound, have intensity of about 1 times 10 power of negative 12. W is watt per meter square. Okay, so why watt? Because we have intensity in the unit of power per unit area. Okay, watt is the unit for power, and then m square is the unit for area. That means the faintest sound. Okay, the faintest sound, the least that our human can hear is is the intensity of 1 times 10 power of negative 12 watt per meter square. While at the same time, that is also known as threshold of hearing. So there are some terms that we use to um, what we call the as there's some term that can we use in sound wave so that it represents something, because the threshold of hearing is 1 times 10 power of negative 12 watt per meter square. So this is the constant value. The loudest sound, however, at the same time, the loudest sound we human can tolerate have an intensity of about 1 watt per meter square, 1 watt per meter square, and it is called a threshold of pain. This is the faintest sound, the least that we can hear, and this one, in terms of intensity, of course, in terms of intensity, and this one is watt, 1 watt per meter square is the least that, well, okay, or so I call it the loudest sound that the human can tolerate, which is 1 watt per meter square, and also known as threshold of pain. Okay, these both are the constant value. So you should know both have is a constant value. For those who want to understand the threshold of hearing and threshold of pain, we can look into the examples afterwards. Okay, the threshold of hearing, okay, the increase in pressure in the ear, okay, let's see, approximately at about 3 times 10 power of negative 5 Pascal. PA stands for Pascal over a pressure of atmospheric pressure at 1 times 10 power of 5 Pascal. So we can say that because atmospheric pressure is about 1 times 10 power of negative 5, 10 power of 5 Pascal, this means the ear can detect a pressure fluctuations as small as about 3 parts in 10 power of 10. Ear can detect pressure fluctuations, okay, as small as 3 parts in 10 power of 10. Very small. Okay, so the maximum displacement of an air molecule at the threshold of hearing is about 1 times 10 power of negative 11 meters. Okay, the maximum displacement of an air molecule at the threshold of hearing. Okay, this is about threshold of hearing. Okay, at about 1 times 10 power of negative 11 meters. Okay, we can see here it's not equal, but it's about. Okay, because yeah, the symbol is like this one. Okay, with a wavy equal, so it's about. That means it is not approximate value. Okay, it's just some value that we consider to be at about, right? So now we look at another comparison. If we compare this displacement with the diameter of a molecule, which is about 10 power of negative 10 meters, okay, so we see that the ear is an extremely sensitive detector of sound wave. Okay, it's a very sensitive detector of sound wave. Okay, now let's look at the threshold of pain. So the loudest sound the human can hear can tolerate at about 1 kilohertz. Okay, 1 kilohertz correspond to the 1 kilo, that means 1000 hertz. Okay, correspond to a pressure variation of 29 Pascal over an atmospheric pressure with a maximum displacement of air molecule at about 1 times 10 power of negative 5 meters. Okay, so that is quite a value. Now, all right. So today we have learned about intensity, but there is also a value that we should consider when discussing about speed of sound. This is what we call as intensity level. Okay, it's quite the same as what we learned before this, which is intensity and intensity level. So now you need to look at the value because we have intensity and also intensity level. Intensity in the unit of watt per meter square. But intensity level, okay, we need to see the sound, the intensity level in decibel, the unit of decibel. I'm sure you're quite familiar with the decibel because that is the that we use in decibel level. That's why we need to differentiate between intensity and intensity level. It seems the loudest tolerable sound that have intensity of about 1 times 10 power of 12 times greater than the faintest detectable sound. Okay, that being said, we don't perceive the most intense sound as being 10 power of 12 times louder than the faintest sound because the sensation of the loudness is a logarithmic in the human ear. Okay, so the relative intensity of sound is called intensity level. The relative intensity of sound is called intensity level, or sometimes have been known as decibel level. So intensity level there are different units compared to intensity, because in intensity we're considering power over area, so power is watt and area is meter square. But in intensity level, we use decibel and some logarithmic values. Okay, how to calculate the intensity level? So we need to take the constant I naught as the reference intensity. In this case, I naught is the threshold of hearing. Okay, because I naught is 1 times 10 power of negative 12 watt per meter square. Then we need to put it here as a threshold of hearing. That means the faintest sound the human can hear. And B is the corresponding intensity level where you should measure B in decibel. So stated here, we need to calculate beta, it's called beta, as a 10 of log, okay, 10 of log, which is the basic log of I over I naught, where I is the intensity and I naught is the intensity, is the threshold of hearing, which means we use 1 times 10 power of negative 12 watt per meter square. And because intensity, we have calculated earlier, considering a certain value, which is we might get intensity in the unit of watt per meter square. So there is also we can find the solution for this logarithmic problem. Okay. So the word decibel, which is 1/10 of a bell, comes from the name of inventor of the telephone, Alexander Graham Bell, who lived from 1847 to 1922. Okay, right, it's very good to understand this one. Let's get a feel for various decibel level, right? Okay, so first let's substitute the threshold of hearing of intensity for this one. Okay, from this result, we see that the lower threshold of human hearing has been chosen to be 0 on the decibel scale. How possible is 0? So when you put it as beta equivalent to 10 log of I over I naught, remember, okay, in the previous slide, we happen to have some equation of beta equals to 10 log I over I naught, where the I naught is 1 times 10 power of negative 12. So as the first problem, we took I, okay, this one, okay. So this one is I, okay, I, which is at 1 times 10 power of negative 12, which is the threshold of hearing, the same as the bottom part, because the bottom is always I naught, okay. Bottom is always I naught. And the I naught is the threshold of hearing, the same number, right? So we may get, okay, we cancel out and we get 1. So 10 log 1 is equivalent to 0 decibel. Okay, if we took another value, for instance, we have continue to intensity by power of 10. So we reduce the number of 1 times negative 12 to 10 power of negative 11. So now we may see 10 is equivalent to 10 decibel. dB is the unit for intensity level. That is what we call as decibel. So as the intensity goes down or increase, because 10 power of negative 12 is the least one. So when 10 power of negative 11 is actually, the number is decreasing, but it's actually increased because we have uh, cancel out 1 0. Okay, so 10 power of negative 12 and 10 power of negative 11. 10 power of negative 11 is bigger compared to 10 power of negative 12. In terms of number, 10 power of negative 11 is bigger compared to 10 power of negative 12. So when we decrease, so when we increase the value from 10 power negative 11 to 10 power of negative 10, you can see look here, okay, at the bottom part, at the denominator part, the number is still the same because this I naught, which is what we call as threshold of hearing. Okay, but on the nominator part, okay, on the upper part, okay, it have been increased to from negative 12 to negative 11 to negative 10. As you can see, the intensity level is increasing. So you need to use your calculator to find the logarithmic problem. Okay. So for instance, if we use a threshold of pain, we want to know what is the decibel for threshold of pain. So we took 1 because a threshold of pain I equivalent to 1 watt per meter square. Remember the unit is 1 watt per meter square, and the bottom part is still, the denominator part is still the threshold of hearing. So we might see that this equation, so you have the power of 12, the power of 12, you get to this, okay, to the, we get 12 times 10, so you will get at about 120 decibel. So at the threshold of hearing, the decibel is 0, and the threshold of pain, the decibel is 120 decibel. Okay, now we may look at the sound intensity level, okay, the approximate intensity level of different sound. For example, the threshold of hearing, the intensity level is 0 decibel. Okay, from threshold of hearing, it moves to the rustling leaf. Okay, that means the sounds of the leaf rustling. Okay, that means we took a one leaf and we took a wet leaf. Okay, we try to uh, find the rustling leaf. So it's about 10. Whisper, bisip, is about 30 decibel. Mosquito buzzing is at about 40 decibel. A normal conversation, okay, normal conversation as we did now, okay, is quite a 50 decibel. Vacuum cleaner is about 70 decibel. Okay, a busy traffic at about 80 decibel. Subway power mower, okay, subway power mower is about 100 decibel. And lastly, okay, siren or rock concert, okay, will have about 120 decibel. 120 decibel is actually we reach at the threshold of pain. This is threshold of pain where I equals to 1 watt per meter square. Okay, because we have calculated earlier, and the threshold of pain will give you 120 decibel. But there is still a lot of decibels on top of it, which is the jackhammer or the machine gun is 130 decibel. And lastly, a nearby, not close to you, a nearby jet airplane, okay, airplane jet that contains about 150 decibel. As you know, this is some approximate value, not the the equal value. Okay. So we can see here there's a lot of intensity level. There's a lot of different sound. We give some intensity, and also it will give a different intensity level. As you know, the intensity level is a beta equals to 10 basic log over I over I. I is the intensity, where I naught is the intensity, sorry, the threshold of hearing. Okay, let's look into the examples. Let me see. A noisy grinding machine in a factory produces a sound intensity. Look at the value, sound intensity. So this is your I intensity. Calculate the decibel level. That means the question will ask you to find the intensity level of this machine. So we use the beta equals to 10 log I over I naught. So you put the I, and then you will find the intensity level is equivalent to 70 decibel. Okay, so don't worry about the how they did. So they took the 7, okay, go to this part, and then you will get, okay, you multiply with 10 because 10 is in the front part of the value. So you 7 multiply by, because 10 log basic, that means this is already 10 log. So 10 log 10 is equivalent to 1. So 7 times 70, so you will get 70 decibel. Okay, in part B, the new intensity level when a sound identical machine is added to the factory. A same but identical machine. That means from one, you have two machines at one time. So you multiply it with two. Multiply the intensity level by two. So you take two, okay, 10 power of negative 5 watt per meter square. You take both, okay, okay, because that is considered to be you have two identical machine. So the value is will get higher intensity because the intensity have increased to 2 times 10 power of negative 5. How do I get 2? Because 1 times 10 power of negative 5 multiplied by 2. Okay, remember this one is I, okay, multiply by 2. Okay, you multiply it by 2. So to get 2 times 10 power negative 5, and then you do the same, the same problem, same things you did in here to find the 73 decimal. And then part C, a certain number of additional such machine are put into operation alongside these two machines. When all the machines are running the same time, the decibel level is 77 decibel. Find the sound intensity. Now we need uh, to find we need to uh, uh, we need to reverse back, okay, our calculations by using beta equals to 77 degree 77 decibel. So from decibel we need to reverse our uh, calculations to find the intensity of I, which is you need to use 7.7 because 10. Okay, so you need to find I, the intensity. So in this case, the intensity is equivalent to 5.01 10 power of negative 5 watt per meter square. So we need to reverse by our calculations. Okay, so in this case, there are two main things about calculations in the case of sound. Number one is the sound, the intensity of sound. Intensity is given by the equations of power over area. Okay, power over area. How do I know power? Because power comes from energy over time. Okay, that means you produce some energy over a certain time. For instance, we are heating a tuning fork that is considered to be our energy at the particular time. So we use a power and over an area, so we get the intensity. And so from the intensity, we can calculate the intensity level. How do we calculate intensity level? We use the intensity level equation, which is beta equals to 10 log of I over I naught. I over I naught, where I is the intensity that you want to find, and I naught is the threshold of hearing. And of course, the threshold of hearing is always 1 times 10 power of negative 12 watt per meter square. Okay, so from that we can manage to find the intensity level, or like this one, like these examples. Okay, in part A and part B, part A we have some machinery, the single machinery, and in part B we have a double machinery. So we can see the decibel have been increased from 70 to 73. And lastly, we have we should reverse back our calculations to find intensity if all operating machine have increased the decibel to from 73. So I don't know, maybe from the level of 70. And lastly, the intensity level at 77. So you need to get the eyes here. Okay, so you need to reverse back all the calculations to find the intensity is about 5.01 10 power of negative 5 watt per meter square. Okay, um, so this is the spherical and plane wave. Okay, so maybe I will discuss this in our class tomorrow, inshallah. Okay, I will not. We will. Okay, we will only discuss until the intensity level for today, I believe. Okay, that's enough for today because okay, you need to digest first the intensity level before we can come to this part. Okay, the spherical and for plane wave. Right. So I think I'll stop here, inshallah. Okay. If you do have a question, do you have a question?